All right, we're continuing with chapter 4, which is on the graphs of the trig functions. In this video, we're going to go through section 4.4, which is on the graphs of the secant and cosecant functions. All right, so similar to what we did in the previous section, when trying to understand tangent and cotangent, let's think about the definition of the trig functions with respect to secant and cosecant. All right, so here's the initial side. Let's draw the terminal side at some random orientation. I like the third quadrant because that seems like the most random, but you could put it anywhere. This terminal side and initial side define an angle theta, and that's what we're going to be calculating the trig functions of that angle. Make a triangle. Okay, there is the reference angle. So this point here has coordinates x and y. The hypotenuse is r. Okay, so the secant of this angle, secant of theta, we know is the reciprocal of cosine. So cosine is x over r, so secant is r over x. Okay, and then cosecant of theta is the reciprocal of sine, so that's going to be r over y. So let's think about what happens. Let's start with secant. So the x-axis is theta, the y-axis is secant theta. Starting at theta is equal to 0, what happens as we progress around the circle with secant? Well, we're already familiar with this. We went in a previous section. We talked about the domain and range of all the trig functions, and so if you remember, so thinking about the range of sine and cosine was -1 to 1. Okay, and then the range of secant and cosecant was 1 to infinity. And why is it 1 to infinity? Well, okay, so at theta is equal to 0, we know that y is equal to 0, so cosecant is undefined. But then if we think about it, though, when theta is really close to 0, y is really small. Either, thinking about if, let's say, theta is just above the x-axis, so y is a really small positive number, and r is constant for any angle. So some finite, and it's positive. So some finite positive number divided by a really small positive number, that's asymptote behavior. That's going to infinity. So we're gonna see asymptotes with secant and cosecant, just like we saw with tangent and cotangent. But we didn't see, there was no asymptotes with sine and cosine, right? And then with asymptotes, as we know, secant and cosecant are undefined at certain quadrantal angles. All right, so, but thinking about secant, I mean, we can kind of let's think about secant and cosecant on the same graph. So thinking about secant, at theta is equal to 0, x is equal to r, so you have r divided by r, secant is 1. And then as you increase from there, what's happening? Well, r is staying constant, but x is getting smaller and smaller and smaller until x approaches 0 when you approach the pi over 2, the vertical. So you're going to positive infinity because you have positive, r is always positive divided by a tiny positive number, right? So we're going to have, when it comes to, okay, maybe I can let's do secant for the moment. So if this is pi over 2, we're going to have we're going to start off at, this is 1, okay? As we go from 0 to pi over 2, we're going to be doing this, okay? And it seems that it's kind of similar to tangent. If we go, let's, instead of going past pi over 2, let's come back and go towards negative pi over 2, because it looks like the curve is going to be continuous. It looks like we're going to have the same type of period between minus pi over 2 and pi over 2. So maybe secant and cosecant are going to have a period of pi. Let's see. So, okay, as we go in the other direction, so yeah, we can go to negative infinity. So the range of secant and cosecant is minus infinity to 1, and then 1 to infinity. So nothing between minus 1 and 1, but anything outside of that. So as we go in the other direction, you have it's r divided by a, let's see, when theta is negative with secant, you're going to have r divided by still positive x. It's going to be start at 1, and then x gets smaller and smaller and smaller all the way until you have like r divided by a really small positive number. So it does the same thing going to minus pi over 2. It's the same behavior. All right, so it looks like it's going to have a period of pi, just like tangent and cotangent. All right, so if let's go, what happens after we go past pi over 2? Well, then you've got a negative, a tiny negative x divided by a positive, or r divided by a tiny negative x. That's negative infinity. Huh. So no, it's not going to be period pi, because we're going to be starting off down here. And this is something distinctly different than what we just drew between minus pi over 2 and pi over 2. So, okay, so then it goes from, let's see, then x gets bigger and bigger and bigger all the way till x is equal to r, but x is negative. So we go towards negative 1, and we do this. And then when we go past pi, it gets, let's see, it's positive r, and then x is getting smaller and smaller and smaller, so you're going back towards negative infinity. And that's what happens when you get to 3 pi over 2. Another vertical asymptote. Okay, now the fourth quadrant, well, we already did the fourth quadrant. We after we drew the first quadrant, we went back to the fourth quadrant. So we know when we cross 3 pi over 2, we're going to be doing this. So, okay, the period we can see is actually 2 pi. It's 100% going to be periodic. Every trig function, based on the definition of trig functions, will 100% be periodic. At the very least, it will have period 2 pi. But it potentially could have a period less than that. In this case, no, the period's going to be 2 pi. It's the period consists of 2 like vertical asymptote intervals. Like all of this is a period. Okay, so now we expect cosecant to be extremely similar, just like tangent and cotangent were similar, but they're going to be like shifted relative to each other. So cosecant, let's see, when we're going to have an asymptote at x is equal to 0. So r over y is 0, and then you're increasing towards y. When theta goes towards pi over 2 from 0, you're going from, let's see, that would be positive infinity, I'm thinking, right? Because it's positive r divided by positive y when theta is greater than 0. So, yeah, it's going to be, okay, so here's 1. It's going to be like this. And so we expect it to do that. It's going to be the same behavior, and this should be, when you get to, this should be pi, right? Because you get to, this is going to be 1 because you have y is r divided by r is 1, and then you go in the other direction, and y is still positive, as in y is going towards 0, so you're going towards positive infinity. And then we expect this. And then this will let's see. This is at, this next vertical asymptote is at 2 pi. And that makes sense because, okay, when we get here, we're at positive infinity. Then when we cross over, we have a small negative number, or r divided by a small negative number, that's negative infinity. We increase towards -1 because you have r divided by r, but y is negative, and then it increases back towards negative infinity. So yeah, there you go. Period 2 pi, but it's just like tangent and cotangent, but this is shifted. Cosecant is shifted to the right by, it should be a half or a quarter of a period. Yeah, quarter, it's shifted to the right a quarter of a period. With the case of tangent and cotangent, it's shifted to the right a half of a period, which is interesting, right? Because here, this is it's shifted to the right pi. They're both shifted. Cosecant is shifted to the right pi over 2 relative to secant. Cotangent is shifted to the right pi over 2 relative to tangent. But since the period of secant and cosecant is 2 pi, the period of tangent and cotangent is pi. Okay, so now let's get into this section and see what else we can learn about the graphs of secant and cosecant. All right, graph of the secant function. Consider the table of selected points accompanying the graph of the secant function on the next page. These points include special values from minus pi to pi. The secant function is undefined for odd multiples of pi over 2, and thus, like the tangent function has vertical asymptotes for such values. Okay, and then secant is an even function. So cotangent and tangent were odd functions. Secant, and I believe cosecant as well, is an even function. So you plug in minus x, you get the original function back. Right, if we come back here, yeah, cosecant is going to be even as well. So it even means you're symmetrical about the y-axis, right? You flip about the y-axis, you're on the graph. Flip about the y-axis, you'll be on the graph. And the algebraic way of looking at that is you plug in minus x into the function and you get back the original function. Okay, so here they use some special angles as inputs and plot some points. So this is from minus pi to pi, which is a full period. That's 2 pi, but this is, you know, just another way of looking at the period. The way I was describing it, you would start here and finish this off. I was looking at that as a period, but you could look at it this way too. Any going from 1 point to 2 pi is going to be a period. Because secant values are reciprocals of corresponding cosine values, the period of the secant function is 2 pi. So yeah, we could have guessed that the period was going to be 2 pi, since it's the reciprocals of secant and cosecant are the reciprocals of sine and cosine. Okay, when cosine x is equal to 1, the value of secant x is also 1. So yeah, if we come back, we know that so secant at theta is equal to 0, what happens? X is equal to r, so secant theta is equal to 1. Well, okay, what's the reciprocal of secant is cosine. When theta is equal to 0, what's cosine? Well, x is equal to r, so they're equal. They're both equal to 1. And same idea with cosecant and sine. And if you think about it, that's the only time the two functions are going to, the two corresponding functions are going to be equal at either 1 or minus 1. Anytime secant or cosecant equals 1 or minus 1, then the corresponding sine or cosine is also going to be 1 or minus 1. And we can see that here. So this is secant, which the reciprocal is cosine. And you can see if you go ahead and draw the cosine curve, which has range between from minus 1 to 1, so you can draw it in between the secant. Every time when either cosine or secant equals 1 or minus 1, the two curves touch. But anywhere else they don't touch, so they're only equal at those values, at the peak values, the peak and trough values of the sinusoid. Okay, so now here they give a summary of the secant function. The domain is, you can't have, with secant, it's the verticals is where you run into asymptotes. Because secant, you're dividing by x. So when at the verticals, x is 0. So it's undefined at, this 2n plus 1 times pi over 2 indicates any vertical. or any angle coterminal with a vertical, and the range minus infinity to minus 1 and 1 to infinity. Okay, and then let's see. Discontinuous had the vertical asymptotes, right? There's no x-intercepts, which makes sense because think about the range. Period 2 pi. There are no minimum or maximum values, so its graph has no amplitude. Yeah, so I mean, they do have these peaks and troughs, but what they're saying here is like cosine never went past 1 or below minus 1, went above 1 or below minus 1, right? It had these like absolute maximum and minimum values. Well, secant and cosecant go off to positive and negative infinity, but they do have these, they do kind of, in some sense, they do have peaks and troughs though. And then it's symmetric with respect to the y-axis, so it's an even function. Okay, as we shall see, locating the vertical asymptotes for the graph of a function involving the secant is helpful in sketching its graph. Yeah, just like with tangent and cotangent. All right, cosecant. They do a similar analysis for cosecant, but we already have an idea of what's going to happen here. It's just like a shifted version of secant, just like tangent. However, as far as like flipping, tangent and cotangent were flipped relative to each other. Flipped, you could say flipping about the y-axis, like or the x, because they were odd functions, but you could think about kind of flipping about the y-axis. Well, this is probably going to be odd. Well, okay, but yeah, this looks like it's going to be an odd function, but even if you wanted these shapes here are symmetric with respect to a vertical, right? This isn't symmetric with respect to a vertical, so you can flip it about a vertical. But there's no flipping this about a vertical. So the only way to think about it is that cosecant is just a shifted version of secant. It's shifted to the right by pi over 2. And therefore you can see what happens just by doing that simple shift. Yeah, this is definitely going to be an odd function. Flip about the x, flip about the y, you're on the graph. Okay, and then, so here they plot sine, and just like with secant and cosine, they're equal at the peaks and the troughs. Now, not the secant. Yeah, we're talking, this graph here is referring to the sine and its reciprocal. Okay, so they're equal at the peaks and the troughs, 1 and minus 1. All right, so undefined at the horizontals in pi, range minus infinity to minus 1, 1 to infinity. Okay, no x-intercepts, period 2 pi, no maximum or minimum values, and then it's an odd function, odd. That means it's symmetric, but the origin, just like tangent and cotangent those were both odd functions, interestingly. So odd function means you plug in minus x, you get minus the function. Okay, here it says calculators do not have keys for secant and cosecant. Yes, they do. Today's calculators do, so you can easily plot, again, I've got my calculator, I can easily get to any trig function. So if I wanted to do, plot cosecant, there you go. I could do the full graph. Let's see. F1, that was cotangent. Let's do, so cosecant, let's do sine. There you go. Yeah, today's calculators are powerful. So there's no need to, this is saying there's no cosecant or secant that you can use with your calculator. You have to use the reciprocal, but that's not true anymore. Okay, guidelines for sketching secant and cosecant. Yeah, to me, we're just going to, it's like they said, get the asymptotes. Figure out where the period's going to be stretched or shrunk. So figure out how the period has changed from 2 pi. Then if there's any horizontal shifting, see where we're gonna start with if it's unshifted horizontally, we're gonna start with the standard interval of what we'll say with secant, it will be from minus pi over 2 to minus pi over 2, right? 2 pi. For cosecant, we'll say it's from 0 to 2 pi. That will start there. And then if it gets shrunk, we'll kind of stay in that same interval. But then if it gets shifted, we'll think about, okay, 0 to 2 pi got shifted to what position, and then we'll sketch the period there. So yeah, that's going to be the strategy. I don't see what they would say different here. Once you get the vertical asymptotes, then you just sketch. Let's see, how would you sketch what's within the period? Yeah, the typical U-shaped functions, right? You know at the middle of the asymptotes is going to be where it gets to 1 or minus 1, and then we could pick some points, the quarter points, to help us with the shape of the U. Yeah, so you'll get a good feel for this when we work example problems. Okay, like the graphs of the sine and cosine functions, graphs of secant and cosecant functions may be translated vertically and horizontally. Yeah. So, like, okay, here we would, it's scaled up about the x-axis by 2, so the period is 4 pi. And this is secant, so we're thinking about going from minus pi over 2 all the way back to minus pi over 2. But then it's scaled up by a factor of 2, so the period is 4 pi, but we're still going to be sketching it going from like, so when we think about going from minus pi over 2 all the way back to, well, yeah, it would be all the way back to, so minus pi over 2 to, not back to minus pi over 2, but to, let's see, 3 pi over 2. So minus pi over 2, so pi over 2, and then, right, we're back. This is 3 pi over 2 is coterminal with minus pi over 2. So then we would have, these would be the two, intervals, right? But the period has gotten scaled up by 2, which means that we're going to have this distance from here to here, instead of being 2 pi, is going to be 4 pi. And now we went, let's see, it's a quarter of the way, okay, this is 4 intervals. 1, 2, or no, let's see, it would be, yeah. Imagine this is like an invisible line here. 1, 2, 3, 4. So of the total period, this is 3/4 of the distance. This is 1/4 of the distance. So now it's going to be 4 pi. This is going to be 1/4 of 4 pi. This is going to be 3/4 of 4 pi. So this is going to be from, we're going to have minus pi, and then all the way out to 3 pi. And then this would be pi. You see? Now, if there was a horizontal shift, then we would like shift all of this to the left or the right. There's no shift. The scaling up by 2, we'll just plot some points. So we know we're going to be going from, here's 1, here's minus 1, so we'll have a point here and here at the middle. Now, to guide us in sketching the U, we'll just plot some points. Since this is scaled up, this will be like stretched out. So we'll plot some points at the quarter points and then just sketch it. I'll try and draw a little bit stretched. That's it. Okay, so here, this has just been shifted. So again, it's like we'll draw out the period, even if the period's been scaled, we'll think about drawing it out and then just shift it. And then once the period, this period hasn't been scaled, but regardless if it's been scaled or not, then we just shift it and then draw it from there. It's very similar to what we did with tangent and cotangent. Okay, connecting graphs with equations. So yeah, I mean, it's kind of the other way around. You should be able to look at, we can see here, this looks like a cosecant, right? Because it's not, the secant has the U going through the origin, or x is equal to 0. But similar to cotangent and tangent, this could be a shifted secant, right? But we want to try and specify the simplest formula. So we would say this is cosecant, and then the period is 4 pi. So, okay, we've got something like a cosecant of 1/4 x. Okay, now it hasn't been shifted. Okay, what about scaling? I don't know. I guess we have to plug in some points to see. Or no, not 1/4. It's scaled by 1. It's scaled by 2. It went from 2 pi to 4 pi. So let's see what they put. Just cosecant 1/2 x. They didn't scale it vertically. Yeah. Okay. Here we've got, so this looks like a secant, right? That has that position. And let's see. The period is minus pi over 2 to 3 pi over 2. That's 2 pi. So maybe just secant x, and that's it. Oh, wait. No. Because it's been, this is at 0, this is at 2, so it's 1 plus secant x. It's shifted up. Yeah. Okay, addition of ordinates. A function formed by combining two other functions, such as y3 is equal to y1 plus y2, has historically been graphed using a method known as addition of ordinates. The x value of a point is sometimes called its abscissa, while its y value is called its ordinate. Okay, so addition of ordinates, yeah. Yeah, you match up the abscissas and add the ordinates. Use functions y1 is equal to cosine x and y2 is equal to sine x to illustrate addition of ordinates for, yeah, so you could think about adding functions graphically. It's like, so if this is sine and this is cosine, you're coming to an x value and adding this and this, and that's the sum of the function. Coming to this x value, adding these two, they're the same. Coming here, and it's it's not going to change. It's 0 plus whatever this is, right? That's how you can think about adding functions. You go to an abscissa, a common abscissa, and add the ordinates. This subtracted from this. Okay, let's work some example problems.